Today we study ESA11H, differentiation in physics. We recall the rotation matrix that rotates a vector. For simplicity, we restrict ourselves in two-dimensional case. That case, the rotation matrix is given by this form. Let us consider the rotation of a unit vector along the x-axis, E1 hat. After rotation by an angle of theta, it becomes E1 prime, and that is r theta multiplied by E1 hat. And if we make use of the matrix representation, it becomes 1, 0. After being multiplied to the rotation matrix, the coordinates are cosine sine, and in the case of E2 hat, it becomes E2 hat prime, and that has the components minus sine theta, cosine theta. We'd like to know what happens to the displacement of E1 and E2 from the initial stage to after the rotation. So that can be computed by subtracting E1 prime by E1 hat and subtracting E2 prime by E2 hat. And this is the displacement of the unit basis vector along the x-axis during the finite rotation. In the limit, as the theta goes to 0, we know this is a sector of angle theta, and the radius 1, that is a unit circle. And as the angle theta becomes smaller and smaller, and it will become this arc length is 1 times the theta, and this arc length is almost identical to the tangent. So angle becomes smaller and small, then it becomes this arc length is not curved anymore. It becomes straight, and the length of this string approaches the length of the arc length. And this arc length is always a theta, and in the limit, as the theta goes to 0, this displacement magnitude, the ratio of the magnitude of displacement divided by the angle theta, that is small, approaches 1, because this one becomes a tangent to this circle. And we know the tangent to this circle at coordinate 1, 0 is this direction. All right. Therefore, in this direction, and we know the magnitude approaches 1 because the arc length approaches this string. As a result, the limit as theta goes to 0, this displacement divided by the small angle is identical to this because of this relation. This is the displacement along the x-axis, and this is the displacement along the y-axis. And the final result must approach E2 hat, that is tangent, unit tangent vector. As a result, we find that this ratio, sine theta over theta and cosine theta minus 1 over theta, is completely determined because it is E2. So 0 E1 hat plus 1 times E2 hat. Therefore, this ratio approaches 1 as theta goes to 0. And this cosine theta minus 1 divided by theta as theta goes to 0 approaches 0. So what happens to the case if we choose a point on a circle at the polar angle theta? In that case, this tangent must be perpendicular to the unit radial vector. The same will be true for the ratio of displacement divided by angle at small theta. In here, theta is finite, and we have additional angle delta theta. And if we let this delta theta approaches 0, we have similar relations. The displacement of this unit radial vector during the rotation of a finite but infinitesimally finite angle, delta theta, we have similar relation. We know that unit radial vector ER is of the form cosine theta E1 hat plus sine theta E2 hat. And we know that the unit tangent vector along the direction of increasing the polar angle is E theta hat, it is a minus sine theta E1 hat plus cosine theta E2 hat. As a result, we arrive at the point the ratio of the displacement to that small additional angle of rotation approaches the unit tangent vector. As a result, the displacement can be rearranged to separate the x component and the y component. So we finally obtain the coefficient of unit Cartesian vector along the x-axis and the unit Cartesian vector along the y-axis. Finally, the derivative of cosine and derivative of sine table is completed. Now we have obtained derivative of cosine is minus sine and derivative of sine is cosine. What happens if I take the double derivative? Double derivative of cosine can be computed by taking the derivative twice. We know the cosine theta's derivative is minus sine, and then sine theta's derivative is cosine. As a result, double derivative of cosine is minus cosine. It is identical to the original form except that we have additional sine factor. If I move this one to the left-hand side, we obtained equation satisfy this cosine function. In a similar manner, we can find that sine theta also satisfies the identical differential equation. So second order derivative of either sine or cosine is identical to original function except that we have additional sign difference. As a result, if I multiply this equation by alpha, an arbitrary finite number, non-zero, or either 0 or not, multiply beta and sum them all, then we'll find that there is a function f of theta that satisfies the identical differential equation, and that is a linear combination of cosine and sine. Now, we make use of this differential equation. We rewrite this one, move this guy to the right-hand side. And we remember cosine theta equals 1 at theta equals 0. And we know cosine is the coordinate of a point of a unit circle centered at the origin. So cosine value is oscillating between +1 and -1. It is a finite value. In the case of sine, it still oscillates. It's a y-coordinate value, oscillates between +1 and -1. As a result, we like to make an approximation by making use of powers of this simple argument. That is called the polynomial approximation. We have obtained, for example, we have found this square root of 1 plus epsilon for a very tiny number epsilon, a positive, either positive or negative. If the absolute value is much smaller than 1, then we learn that it can be approximated neglecting order epsilon squared. Something like that. In this manner, we can express some arbitrary function that is finite in powers of a very simple argument. That is called polynomial approximation. All right, we'd like to introduce this polynomial that does not terminate at a finite value, but it can be summed to the infinity. We remember the cosine function, even function. As a result, if I want to expand this, for example, a0, a1 theta, a2 theta squared, and so on, then it must satisfy the fact that it is an even function. So all odd powers contribution must disappear. As a result, our cosine function should be expressed as a sum of even powers of theta. Sure, because cosine 0 equals 1, we can determine the initial term by substituting theta equals 0. So this coefficient, the first coefficient, a0, must be 1. Now we can make use of the fact for any positive integer, derivative of a polynomial is just xn is n times x to the n minus 1. What about the second order derivative? That is obtained by applying this formula twice. As a result, we have n minus 1, and then power is decreased by 2. What about this expression? Why don't we substitute this for the cosine theta? In that case, the summation is still there. We have this one, 2k, and this power is 2k, and multiply 2k minus 1, and this power decreases by 2. So 2k minus 2. All right. By the way, if I substitute k equals 0, this first term must disappear because of this factor. So it's better to shift this k by 1 because it is equivalent to k runs from 1 to infinity, a, 2k, 2k, 2k minus 1 theta 2k minus 2. I'd like to replace this one with the 0. Then I have to add k by 1 instead of k, because the first term appears at 2k equals 1. 2k equals 2. So it begins with k equals 1. If I want to replace this one to make k starts with the 0, I have to replace every k by k plus 1. Then this is replaced with the 2k plus 2, 2k plus 2, and 2k plus 1, and 2k. As a result, we'd like to compare this because this one must satisfy this relation. Second order derivative must be the same as a minus cosine. And minus cosine is minus this one. Let us compare this one and this one. They must be the same. They must be the same. We find a 2k plus 2 is minus a 2k, this one. An additional factor is there. Why don't we divide both sides by this factor? Before doing that, we have the 2k, a 2k equals 2k minus 1, 2k equals minus a 2k minus 2, something like that. As a result, this one can be expressed like that. And we can replace this one using the same relation recursively. If I do this job one more time, and this factor becomes squared, and this index becomes k minus 2. And we have additional factor decreases by 1. So we have 4 factors, and so on. We keep doing this until this 2 reaches the same value as k. Then, when this 2 appears, this power was 2. Therefore, if I have 2k minus k, my power of minus 1 is k. And finally, the denominator begins with 2k and factors decreases by 1 until the end. The last factor was 2 times 1. And we know this is 2k's factorial. Finally, this is a 0 that we know that is 1. If I substitute this relation for a to k to the original expression for cosine, we end up with the infinite sum of a power series of theta. In a similar manner, the sine theta can also be approximated with the powers of theta. And we know this is odd and this is even. Okay, that's it for today. Thank you.